In the last lesson, we looked at Lewis dot diagrams of ionic compounds. And while we can draw those, they're not as helpful as Lewis dot diagrams of molecules. So we're going to look at now Lewis dot diagrams of molecular compounds. From the formula of some molecules, it's not easy to interpret how the atoms are bonded together. So for instance, methane C3H8, that formula doesn't tell us anything about how the carbons and hydrogens are bonded together. So what we need to look at is bonding capacity, and that's the maximum number of single bonds or number of bonding electrons for an atom. Once we know that, we'll be able to interpret and put together molecules much easier. So if we look at the examples that are on this table, there are atoms carbon, nitrogen, oxygen, halogen, and hydrogen. And from the number of valence electrons of the atom, we can figure out the bonding capacity or number of single bonds that those atoms can form. So carbon in group 14 has 4 valence electrons. That means it has a bonding capacity of 4. It can form up to 4 single bonds. Nitrogen has 5 valence electrons. 2 of those are a lone pair, which means 3 of them are bonding electrons. Nitrogen can form 3 single bonds. Oxygen has 6 valence electrons. 4 are lone pairs. Only 2 are bonding electrons, so oxygen forms 2 single bonds. All of the halogens in group 17 have 7 valence electrons, which means they have 1 bonding electron. And hydrogen has 1 valence electron and therefore has a bonding capacity of 1. Hydrogen only ever forms 1 single bond. To draw Lewis dot diagrams of molecules, we need to draw the Lewis dot diagrams of the atoms and start bonding them together. So the first step is to draw the Lewis dot diagram of the atom with the highest bonding capacity. If you don't remember the bonding capacity of the numbers, the easiest way to think of this is to work from the middle of the periodic table or closest to the staircase line and out towards the right-hand side. Second step is to start drawing and attaching the Lewis dot diagrams of the atoms with the next highest bonding capacities. So again, starting from the middle, working our way outward. Once all of the atoms have been drawn with their electrons, then we can move unpaired bonding electrons from adjacent atoms to form multiple bonds. And we'll see this as we do a few examples on the next page. So here are 4 examples. We're going to build these molecules using the rules of the Lewis dot diagrams. The first example, phosphorus trihydride, pH 3. We need to start with the atom that has the highest bonding capacity, and that's the phosphorus. So we start with our central atom as phosphorus, P, and looking at the periodic table, it's in group 15, so that means we draw 5 valence electrons. First 4 go into the 4 separate orbitals, and the 5th one pairs up with the first one that we drew. Now we want to place our hydrogens onto our phosphorus. We need to bond them together, which means we need to pair up those unbonded electrons, those bonding electrons. So 3 hydrogens. First one is going to go on the right, second one will go at the bottom, and the third one will go on the left. Now the phosphorus has 8 electrons, so its octet is complete, and hydrogen has 2 electrons, which is what it needs to have a full valence energy level. Next to that, B, H2S. Again, we want to start with the highest bonding capacity atoms. That's the sulfur. Sulfur is in group 16, so we draw 6 valence electrons. Next, we put in the hydrogens. So again, the electron on the left and the bottom are where we need to form our bonds for the hydrogens. Our third example, carbon dioxide, we want to start with the highest bonding capacity atom, and that's carbon. So we draw carbon with 4 valence electrons. Now we want to bond the oxygens. Oxygen has 6 valence electrons. First one we can use to pair up with the carbon. That creates the bond that attaches the oxygen to the carbon. So when we draw in the 6 valence electrons, we're left with that. Second oxygen, we need to do the same thing. So on the left-hand side, again, we do the oxygen and 6 valence electrons. At this point, our diagram isn't complete. We have electrons that haven't been paired up yet. So what you want to look for are those electrons that haven't been paired up on atoms that are side by side. For the oxygen on the left, that's the electron at the top. And you'll notice that the same thing is occurring on the carbon in the middle. There's an electron on the top that isn't paired up. So those two electrons can be moved so that they form a pair between the oxygen and the carbon. That creates a multiple bond. Now 4 electrons are being shared between the oxygen on the left and the carbon in the middle. We can do the same thing with the oxygen on the right and that electron on the carbon that was at the bottom. So those electrons move, and now again we have a double bond between the carbon and the oxygen on the right. Now each of the atoms has 8 electrons, so the octet rule is complete, and we don't have any unpaired electrons left in our picture. Last example, CH2O. Starting with the atom with the highest bonding capacity, that's going to be carbon. So carbon with 4 valence electrons. Our next atom with the highest bonding capacity is the oxygen. Doesn't really matter where you put the oxygen, I'm going to put it on the right. So oxygen has 6 valence electrons. The first one forms that bond with the carbon so that they're attached, and 6 in total. Now we have 2 hydrogens that need to be placed. We can't put them both onto the oxygen, and if we put them one onto the oxygen, one onto the carbon, we're going to end up with 2 electrons on the carbon that can't be paired up together. So we need to put both of the hydrogens onto the carbon. Doesn't matter which side you choose. So I'm going to do the left and the bottom. Now what we have is an unpaired electron on the carbon and an unpaired electron on the oxygen. Because they're on adjacent atoms, we can move them to form a multiple bond. So the oxygen and the carbon electrons move and form a double bond between the carbon and the oxygen. The last thing we want to look at is a line diagram or line structure. This shows the atoms and bonds within a molecule but doesn't show all of the valence electrons. So if we look at the same molecules that we had on the last screen and draw them as line diagrams, we want to show the bonds with the atoms, but not the lone pairs. So phosphorus we drew as P in the middle and 3 hydrogens. Now instead of drawing the electrons that are being shared, for each pair or 2 electrons, I'm going to draw a single line. So as a line diagram or line structure, this is what pH3 looks like. Second example, H2S, we had 2 bonds, each of those single bonds to the hydrogens. So there's H2S. We don't need to draw the lone pairs that are on the sulfur. Example C, carbon dioxide, we had double bonds between the carbon and the oxygen. So carbon in the middle and sharing 4 electrons, which means 2 bonds or a double bond, goes to each oxygen. And the last example that we drew, carbon was in the middle. We ended up sharing 4 electrons, so creating a double bond with the oxygen that was on the right. and then a single bond to each of the hydrogens that was attached to the carbon. So there are the line structures for the four molecules we looked at on the last screen.